Welcome to lesson 8.2, similar triangles. So if you'll recall from 8.1, two polygons are similar if corresponding sides are proportional and corresponding angles are equal, which means that in general, we need to check every single side and every single angle in two polygons to be able to determine if they are similar. However, let's talk about the special case of triangles. Do we need to check every angle and every side in a triangle? Well, the answer is no, because we didn't need to check that much, even for seeing if two triangles were congruent. Remember that to show two triangles are congruent, we only need three pieces of information. It could be side, 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 angle, 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 side. But in either case, we only needed three pieces of information. And because two triangles being similar is less restrictive than being congruent, that three bits of information will also be good enough here. As long as it's the right pieces of corresponding information. Right, so just like for proving congruence, we only need three pieces of information for triangles. So if two triangles have all three of their corresponding angles equal. So we're looking at a triangle that could grow or shrink, but that's going to be enough to make sure that their sides are proportional. So let's talk about the next one. If two angles of a triangle are equal to two angles in another triangle, then must the triangles be similar? So let's draw that. Right, so I have some triangle ABC, some other triangle A prime, B prime, C prime. I know that A and A prime have the same size angle. B and B prime are also equal. So, do these triangles have to be similar? Well, if this angle is the same as this angle, and this angle is the same as this angle, then because these three angles add up to 180 degrees in each case, the third angle must equal the third angle. So our answer here is yes. Because angles in a triangle add up to 180 degrees, the third angles are also equal. And therefore, the lengths are proportional, just like we said in part A. And that's everything we need to show similarity, that all the angles are equal and all the sides are proportional. What about this next situation? If one angle of triangle ABC is equal to the corresponding angle in A prime, B prime, C prime, so I have A, B, C, A prime, B prime, C prime, and we know that one angle is equal to the corresponding angle. Do the triangles have to be similar? Take a moment to think about it before I give you the answer. So it turns out that this is not the case. So let's do an example. What if we have angle B being 100 degrees in each case? Well, here I could have angle A and angle C both being 40 degrees. That adds up to 180. But I could also have 50 degrees and 30 degrees. That adds up to 180. So these two triangles are not similar. So I've given a counterexample that these two triangles are not necessarily similar because they do not necessarily have all the same angles. So let's state some theorems for proving that triangles are similar. We've learned, for angles anyway, that all three angles will make make the sides proportional, but two angles is enough to guarantee all three. So if I want to show that two triangles are congruent, I actually only need two angles and no sides, just two angles. So that is our first similarity theorem. If two angles in one triangle are equal to two angles in another triangle, then the triangles are similar. So there's our one theorem with two angles. One angle was not enough, but if you have one angle, how could you, if you had only one angle, you would need some sides to go with it. So if I had only one angle, I could have something like SAS. Remember, SSA and ASS do not work. You could get two triangles that have different angles in them, right? So if two sides of one triangle are not equal but are proportional, because we're going for similarity, to the corresponding sides of another triangle, and the angles between these sides are equal, then the triangles are similar. So we know what happens if we have two angles, we know what happens if we have one angle, and if we have no angles, we will need to know all the sides. And again, we're not talking about equality here because we're not looking for congruence. We're looking for whether they're proportional. Corresponding of another triangle then those triangles are similar. So we really have these three theorems for proving triangles similar. If we have two angles, we're good to go. If we have one angle, we'll need the sides that touch that angle. And if we have no angles, we'll need all the sides. So let's work through some problems. If I have these two triangles, where the sides are A and A prime, B and B prime, C and C prime, and these corresponding angles are all equal to each other, let's go through and say, well, if all the angles are equal, then these are similar. So these triangles are similar. And A prime divided by A, B prime divided by B, C prime divided by C, that's just the definition of proportional. So because these triangles were similar, from our AA theorem, those sides will be proportional. And here we go with the reciprocals. Well, that's still the same proportionality. Again, the triangles are similar by AA, so the sides will be proportional. That's just treating this as the second triangle and that is the first triangle instead of the other way around. Well, what if I wanted to do a ratio of two sides inside a triangle versus two sides inside another triangle? So that's this A over B and A prime over B prime. Does that work? So let's look at these one at a time. I'm going to start with the piece that has all the same bits in it from something I already know is true. I know that A prime over A is the same as B prime over B. So I'm going to do a little rearranging of this to see if I can turn it into this. So my first goal is to make sure my A and A prime are both in numerators, and right now they're not. So I'm going to multiply by A, and I'll learn that A times A prime sorry, the A's cancel. I'll learn that A prime is A times B prime over B. Now, I have A prime and A in the numerators, but all the B's are supposed to be in the denominators. So I'm going to multiply by 1 over B prime and 1 over B prime. And I'll learn that A prime over B prime here equals, the B primes cancel, A over B here, which is what we were looking for. And a similar calculation will work for each of these. So take a moment to pause the video and work out this same calculation for the third one, B over C equals B prime over C prime. All right, let's work on part D. If A is 2, A prime is 7, and B prime is 5, then find B. So I'm going to set up one of these ratios, right? I know that A prime over A equals B prime over B, and so I can plug in these numbers. A prime is 7, A is 2, B prime is 5, and then we have B. I don't like that B is in the denominator when I'm trying to solve. So I'm going to get 7 over 2B equals 5. Trying to get B by itself. So I'll multiply both sides by the reciprocal, 2/7. And I'll learn that B is 10 over 7. Here I have information about B and C. If B is 3, C is 5, C prime is 2, find B prime. So we're looking about B's and C's. So B prime over B equals C prime over C. So B prime is the thing I'm looking for. B is 3, C prime is 2, C is 5. I want to get B prime by itself, so I will multiply by 3 to cancel that 3, and I'll learn that B prime is 6 over 5. All right, let's move on to similarity in right triangles. So this picture shows a large right triangle, which is cut into 2 smaller right triangles by that altitude drawn to the hypotenuse. And we're going to prove that these 2 smaller right triangles are similar to each other and also similar to the large right triangle. So we're trying to show that ADC, this medium-sized triangle, is similar to CDB, this littlest triangle, that ADC, the medium triangle, is similar to ACB, the big triangle, and that CDB, this littlest triangle, is also similar to ACB, the big triangle. So that seems like a lot to prove, but really all we have to do is show a pair of angles in each of the triangles, and that will be enough to show what we want to show. So let me add some color to these triangles. So let's call ACD, this medium triangle, the blue triangle. We'll call CDB the littlest triangle, the green triangle, and then the big triangle, ACB, I'll call the pink triangle. So we've got ADC, the blue, and CDB, the green. So we want to show blue and green are the same. We have ADC, the blue, being the same as the pink, and CDB, the green, being also the same as the pink. So let's go through this. All I need is 2 angles in each triangle. So I'm going to recopy these triangles. We have the big triangle, which had A down here, B over here, C, the right angle at the top. We had the blue triangle, D, the right angle over here, A, and C. And we had the little green triangle, C at the top, D, the right angle, and B over here. Well, we certainly have 1 angle in each triangle. So I'm going to start actually with these first 2 triangles. So what I notice is that angle A and angle A are the same angle. They overlap. So this angle, whatever it is the same as that angle. So by AA, angle, 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 I already have this similarity statement. So I'm going to start this over. I want to give the reasoning in words. Since angle A is the same as angle A, and the top angle and the bottom angle, so these 2 angles are both 90 degrees. Angle ACB is the same as angle ADC, which is 90 degrees. I used 3 letters here because if I look at the original picture, there's more than 1 angle at C and more than 1 angle at D. So we've got these 2 angles, these 2 angles. So we have similarity. This is what I'm looking for. Triangle A was the first angle in the blue, D was the second angle in the blue. ADC will be similar to triangle A was that angle, C was the right angle, and then B. by our angle property. Now I'm going to go between the pink and the green. So whatever this angle B is, that's got to be the same as this angle B here, because it's the same angle. Similarly, angle B equals angle B, and angle ACB is the same as angle CDB, which is 90 degrees. So in the green triangle, CDB, that's going to be similar to our pink triangle. Well, C is like A. D, the right angle, is like C, and B is like B. What about these two triangles? I want to look at these angles here because I need to have, this angle's not the same as that angle. I need a pair of angles. Well, let's look at this triangle. Angle A and angle B. Plus angle B. Plus angle C is 180. Well, I know angle C is 90. Angle A plus angle B is 90. So these two add up to 90. Well, here these two add up to 90, and here these two add up to 90. So these top angles here and here have to be the same as those angles. I didn't want just angle C here. I wanted ACB. But here, these two, angle A plus angle, this top angle, ACD, should also be 90 degrees because the whole triangle has to add up to 180, which means that angle ACD, this one that adds up to A to give 90, has to be the same as B. So that means that this is the same as that. So now I have a pair of angles in the blue and green triangles. So this top angle, ACD, equals angle B, and these angles at D, ADC and BDC, are also equal, they're 90. So my blue triangle, ABC, must be similar to my green triangle. A will be like C, D will be like D, and C will be like B. From that AA property. So I've proved it. I've proved that all these little triangles are similar. So this is a super useful bit of information that when you see right triangles fitted into other right triangles, that you should be able to use the fact that this angle equals itself and that this angle equals itself to get that all of these little triangles are similar to each other. And that will help us calculate lengths. Let's look at number 16. We're given here that this line across is parallel to the base of the triangle, and we want to prove that the smaller triangle must be similar to the larger triangle. So let's mark some of that. We know that this side is parallel to that side, and I'm going to give some actual letters to the corners. Possibly. I don't think I need to. So let's go through. Prove that the smaller triangle must be similar to the larger triangle. So we need two angles. So let me at least label 1 point. I think that will be enough. Nope, we're going to want all of them. So I'm going to have the big triangle be X, Y, Z. And these places that are cut by L, I'm going to call point M and point N. Okay, prove that the smaller triangle must be similar to the larger triangle. Well, angle X is equal to itself. That's this angle up here. And that angle is in this little triangle up top and the big triangle. The next angles I'm going to do are these guys here. So angle XMN has to equal angle XYZ. Well, why is that the case? Well, that's because these lines are parallel and these were corresponding angles. Right, we have corresponding angles with parallel lines, so those angles must be equal. So by my AA property, the little triangle XMN must be similar to the big triangle XYZ. So there's my proof. What about A plus B, C plus D, and A? So let's look at this picture a little bit more carefully. A plus B is this big side XY. So XY, the side, that must be, right, A plus B, which is XY, must be in the same ratio with just the little thing here, or sorry, XY corresponds to XZ. And little a, XM, corresponds to no, I'm doing it wrong. XY is this length in the big triangle. And we want that to correspond to the little length in the little triangle. and xz, the length along here, will correspond to the similar length by the definition of similarity that corresponding sides are proportional. But xy was a plus b, and xm was a, xz was c plus d, and xn was c. So we're done. Okay. The rest of these, I don't think I need to look back at the picture. I think I can start from this that I've already proven and do some rearrangement to get these various statements. Okay. So I'm going to start with the thing I know. A plus b over a equals c plus d over c. And I'm going to rearrange this statement. So I'm going to start by splitting up my fractions. So this is going to be a over a plus b over a. I'm using that common denominator backwards to split my fraction. And again there. Well, a over a is just 1. And c over c similarly is just 1. So if I subtract 1 from each side, I will learn that b over a equals d over c, which is what I was trying to prove. Now these are just reciprocals of each other, so let's start here and see if I can rearrange. I know that b over a equals d over c, but I really wanted the a and the c on top, so I'm going to multiply by them. Here the a's cancel, here the c's cancel, and I will learn that c times b is the same as d times a. I really wanted the d and the b to be in the denominators. So I will divide each side by d and b. My b's cancel there, my d's cancel there. And I will learn that c over d equals a over b, which is what I was looking for. Now let's look at what if I wanted a plus b over b and c plus d over d. Well, I'm going to kind of use this backwards. So I wish I had a plus b and c plus d. I'm going to start with this, but I'm going to just put them in the other order so that my a's and b's are on this side and my c's and d's are on the other. So I'm going to start with a over b equals c over d. And I'm hoping that I can move this procedure backwards. So I'm going to start by adding 1 to both sides. And I want my 1's to look like they have a common denominator with that fraction. So b over b plus a over b, c over d plus d over d. Okay, well, what's that? Well, this has a common denominator of b, and the numerator is a plus b. this has a common denominator d, and the numerator is c plus d, and that's exactly what we were looking for. So why did we do all of these manipulations? Well, it shows us that when we cut a triangle with a parallel line, this little triangle is similar to the big triangle, and we have pretty much all the ratios we could possibly want, right? The big sides, a plus b, c plus d, are proportional to the little sides from similarity, but they're also proportional to the pieces that were left over, not even the whole sides of the big triangle. And that just those C and D, A and B are also in proportion. So we have all the sorts of proportionality that we might possibly want in a triangle that's cut by a parallel line, which will help us find all sorts of lengths quickly in future problems. So now you know everything you need to start tackling the classwork and homework.